So here we go. In the previous lecture we discussed uniform quantization, and particularly we were able to find the probability distribution function of the quantization noise, and based on that we were able to find the signal to noise ratio that results from the quantization noise you have in your system based on the number of bits that you use for each level. So in today's lecture we will be talking about non-uniform quantization in the first part of the lecture, and in the second part of it we will talk about line codes. So as the name implies, non-uniform quantization means you don't have fixed step size. The step size is changeable and variable according to the variations in the signal that you want to quantize. Usually it's used in telephonic communication, non-uniform quantization, and this is because the analysis shows that the ratio of the peaks of the loud talks to the peaks of the weak talks is in the order of 1000 to 1. The peaks and weak peaks of the talk, there is a huge difference in the ratio between them. That's why we need to choose and use adaptive step size, where the step size will be small for the weak signal, while the step size will be large for the high fluctuation signal, large fluctuation signals. In non-uniform quantization, step size delta is made variable according to the sample amplitude. So the use of a non-uniform quantizer is equivalent to passing the baseband signal through a compressor and then applying the signal to a uniform quantizer. You compress the signal first and then you quantize normally. Usually we use there are two compression techniques available. The first one we call it MIMO, and the second one we call it ALO. These two compression techniques can be applied to the signal. So in ALO compression, the quantized value V, the absolute value of V, is defined as log 1 plus U magnitude of M divided by log 1 plus U, where U is a constant, actually, positive integer, and M is the actual value of the message, and V is the quantized value. So suppose you have the following, the x-axis here represent the message value, and the y-axis represent the quantized value. And this is the curve resulting from this equation. For example, when you put U equal to 0 and you draw the figure, you get this line. When you put U equal to 5, you get this curve. When you increase U further and put it 100, you get this curve. Yes? So depends on you, the shape of the figure changes. And as you can see here, for low values of the signal, when you increase U, at low values of the message signal, you have large amplification. For example, here, the signal might be, what's the value of the message signal here? 0.1. What's the output? The output is almost 0.5. What do you do basically? You amplify your output. Why do you amplify it? Because the signal is weak. The signal is 0.1. I need to amplify it. While when you go large, there is no need to amplify it too much. For example, when it's 1, it's fine with me. It remains 1. So it amplifies the low values of the message and gives normal values to the large values of the input message. So this is the basic concept of MIMO and the relationship between its formula and the curves that it has at different U values. So we have also ALO compression. In this type of compression, the difference is the equation. We can see that we have two equations for two regions. when the message value is between 0 and 1 over a, where a is an integer positive, then we use this equation. If the message value is a little bit larger, then we use this equation. The difference between them, when m value is small, you tend to magnify the message signal, the output of the compressor, more. But when the m value, the message value is large, you don't need to magnify too much. You just change the equation, change the formula to a different formula that doesn't magnify too much. For example, when a is equal to 1, you have no compression, no magnification, nothing. It's normal. When you have an input value of the message equal to 0.6, the output is 0.6. But when you change a to be 2 and you have the input to be 0.2, then the output is gonna be almost 0.4. So as if you are magnifying, amplifying your output signal, because the message signal is low, the amplitude of it. This is the basic concept. So you just need to understand the relationship between the equation and the figure, and what does this mean, and how I magnify the signal, how I reduce its amplitude, adjust it according to my system. So this is basically A law and the differences from U law. Now, to restore the signal samples to their correct, suppose you performed non-uniform quantization and you sent your signal. Now the receiver has, you must inform the receiver that you have performed A-law or mu-law compression. And for the receiver to restore the signal back to its normal state, he has to know that thing. And to do that, he just performs the opposite of that formula that you used for compression. It's like equalization in wireless communication. You have the channel multiplied by your signal. To remove the effect of the channel, you divide by the channel value so that you get the message back. It's similar here, something similar. Consider the compression equation, the channel, and to remove the effect of this channel at the receiver, you need to normalize it, equalize it, remove its effect. To remove the effect of the quantizer, we use expander. Expander is the opposite of compressor. The combination of a compressor and an expander is called compander. For both U-law and A-law, the dynamic range capability of the compander improves with increasing U and A. We saw this in the figure, yes? The compression and decompression improves when you increase U or A, as you have. If you noticed in the previous figure, for example here, when you increase A for the small values of M, you significantly enlarge the amplitude of the output signal. Significantly. For low values, you have large values. This is what I mean by increasing A and mu. So, the signal to noise ratio for low level signals increases at the expense of the signal to noise ratio for high level signals. Low level signals, what do? You magnify them. So since you magnify, the signal to noise ratio increases for them, while this happens at the expense of high level signals. Because in high level signals you don't magnify, you keep it normal. A compromise is usually made in choosing the value of U and A. If you keep it normal, it becomes uniform quantization. If you change the value of U and A, it becomes non-uniform. Now, non-uniform, you can make it in such a way that enlarges, magnifies the low values significantly or slightly. Depends on your application. Typical values of U, usually in practical system, they choose U to be 255 and A to be 87.6. These are the typical values used in practical systems. So, now we talked about uniform quantization, non-uniform quantization, and we said these processes are part of the PCM modulation, pulse code modulation. And in general, pulse code modulation is the most basic form of digital pulse modulation. Whenever someone talks about digital communication, you have to mention pulse code modulation. It's because it's the basic principle that links, that usually converts analog to digital. From an analog waveform that have continuous values to a digital waveform that has finite set of values. So PCM is accomplished by representing the signal in discrete form in both time and amplitude, not only time, but also time and amplitude. Discrete in time means sampling, discrete in amplitude means quantization. These processes combined together produces what's called PCM, pulse code modulation. PCM can be described by the block diagram shown in the next figure, this is the simplest diagram you can explain PCM block diagram. You have a source of continuous time message signal, you want to send it. After that, you pass it through low pass filter to get rid of aliasing and the interference between consecutive symbol. Then you have sampler, which makes the signal discrete in time. After that, you have a quantizer, which makes the signal discrete in amplitude. After that, you use encoder that converts your levels into bits. So the output here is basically a sequence of zeros and ones. Then you send it through the channel, you send it through wire lines, cables, whatever, and after, for example, 1 kilometer, the signal decays. The signal suffers from the environment. So to make sure that your signal doesn't die, you use repeater that regenerate the signal one more time, amplify it, and send it again. So on the way, repeater keep using repeater until the signal reaches its destination, the receiver. At the receiver side, you have regeneration circuit that reconstruct your signal. After that, you have PCM demodulatory process where you have decoder that converts bits into discrete amplitude levels. And after that, you have reconstruction filter. Reconstruction filter, something like smoothes the things, connect the peaks with each other and perform some kind of smoothness so that you can reconstruct your analog signal and to the destination. So this is basically what PCM is and its relationship to uniform quantization and non-uniform quantization. With this, we finish our discussion about PCM, and then we move next to the line codes, which are important. After you receive line codes here, after you generate your zeros and ones, you need to send them over the channel. You cannot send zeros and ones directly to the channel. You need to convert them. You need to convert them to line codes, which are suitable for a transmission over the channel. Is that right? You cannot send them directly. So in line codes, which is the second part of our lecture, what do? We need to represent the data bits, the sequence that's resulting from your PCM modulator, which is composed of zeros and ones, into what? Into electrical signals using some line codes. There are several line codes that can be used for the electrical representation of binary data stream. Many codes are available, however, we will study here only 5 of them. And a more detailed line, if you want to have more detailed information about line codes and study all their types, you can go to Hyken or Sklar book and read more about them. Actually, they are you can find many other line codes alongside their advantages and their disadvantages. So basically, we'll be discussing unipolar non-return to zero line code, polar non-return to zero, unipolar return to zero, bipolar return to zero, and finally end up with split phase or Manchester code. So these are basically the codes that we will be talking about and discussing during the lecture. So let's go to the first type, which is unipolar non-return to zero. The question can be like this: you have you have this binary sequence, zeros and ones, and for example, your responsibility as an engineer to convert this to a suitable electrical signal that can pass through your channel. Now, your system will have some certain requirements. The company or the customer you want to sell your product for, he will ask you, I want to make sure that there is no DC power. There shouldn't be any power spectral component in the zero frequency. There should be no clocking. There should be no synchronization. The code should work perfectly for multiple users. So based on these requirements, your goal, your aim as an engineer is to find the most suitable encoder that can fit for that requirements. And if you cannot find any of these line codes which are suitable to meet these requirements, you need to invent your own based on making some combination between the available codes you know, or come up with your own line code. So this is the basic concept. This is where you start thinking like an engineer, and your responsibility is to know all these line codes and be able to match them to the requirements of the system, be able to know the advantages and disadvantages of each one of them. And if you encounter a case where you don't have such a line code that can meet all these requirements, you need to come up and invent your own line code. So basically, you start from basics and then you start building up on top of what you know. In unipolar non-return to zero, unipolar, as the name implies, means only in one direction, only either above zero or below zero. You don't have two signs for the signal, zero, plus and minus. So this is, as you can see the signal here, all of it positive. This means it's unipolar. There is no negative side of the signal. Non-return to zero means when you represent digit 1, you don't return to zero. It's positive, whatever the value is, but it must not return to zero. That's why we call this line code unipolar non-return to zero. This is unipolar because it's positive, the signal is always above zero, is always positive. And non-return to zero means when you represent 1, you represent digit 1 by plus something, plus 5, plus 10, plus 9, whatever, but that plus 9 keeps constant over the period of 1 digit. So symbol 0 is represented basically by switching off the pulse. You don't transmit anything. When 0 comes here, see, this is 0, you don't transmit anything, it's just 0. When 1 comes, you just transmit plus A. Another 1 comes, another plus A. Now, what's this code? As you can see, one of the key advantages of this code, it's simple, and it can work for optical channels. Because in optical channel where your source is laser, you are not allowed to send negative signals. You cannot, because there is no such negative thing you can send in laser, in optics. That's why the good advantage of this code can be used for optical channel. But the disadvantage of this line code is the waste of power. Why do we have waste of power? Because it's always positive. And if you find the average, whatever the signal is, you will have a DC value. What's the DC value? It's the expectation of the signal. Yes? The DC value is equal to what? The mean of the signal. Or suppose your signal is X, the mean, which is expectation. Now, if you find the mean of this signal, what would be the mean of this signal? It will be A over 2 almost during this region. So, A over 2 is the amplitude. The power, square it, becomes A square over 4. So this is the waste of power during the transmission of your signal. So if you are limited in power, like for Internet of Things devices, can you use this? It's not recommended because Internet of Things devices don't have too much power resources. They are battery limited. This kind, you need to link the application with the technology and see which one matches for which one. Based on what? Based on the capabilities of the line code and the requirements of your application, and see how they fit to each other. Now, the second type of line codes is called polar, non-return to zero. Now, from polar, what does this mean? This means that the signal can has positive and negative. Yes, polar, because it's polar, two sides. And non-return to zero, also when you represent 1, you are not allowed to go to 0. See, for example, can you guess what's the binary sequence that this signal is representing? With me, 1 by 0, 1, 1, 0, 1, 0, 0, 1. So if someone gives you a signal like this, you are the receiver. You receive this signal, and the system engineer, the system design engineer tells you that we are using polar non-return to zero. Cannot you extract the bits from the electrical signal? You can, because you know the mapping process, you know how the 0 is represented and how the 1 is represented. You just need to demap them. And this is what the receiver does actually. When you inform the receiver that I'm using polar non-return to zero, you receive this signal. The receiver knows, very smart, he knows how to demap. What's the disadvantage of this line code? Is the large power spectrum of the signal near to 0. Now when you take this code and find the Fourier transform of it, you will find that you will have a spectrum component around 0, and this is large. This is actually not good because of filtering issue, and the 0 component, I told you, when the frequency is 0, it cannot pass through your cable. Yes, or through your channel, but cannot propagate at 0, because when you have the value, the frequency is 0, you have constant. Constant doesn't alternate. It's not like AC. It doesn't produce something like a signal that oscillates. That's why it doesn't propagate. Due to this is disadvantage. We don't like to have large power spectrum of the signal near to 0 frequency. Why? Because it's waste of power transmission and doesn't allow for all the signal to pass through your transmission line or cable or your medium. The advantage, on the other hand, it's easy to generate. Yes, very easy. You just if 0 comes, minus A, if 1 comes, plus A. The circuit, you can build a very easy and cheap circuit to produce this. So this is the second type. The third type is unipolar. Now we got a polar, unipolar, and bipolar. Bipolar, we didn't talk about it. We will talk about what does bipolar mean later on, after 2 slides maybe. Now this is unipolar return to 0. What does this mean? Unipolar, the signal is always above 0, is positive. And return to 0 means when you represent 1, the 1 maps to a pulse that part of it goes to 0. So, for example, this signal, you have 0, 1, 1, 0, 0, 1, 0, 0, 1. 1 is actually this pulse. See, I'm highlighting it. So as you can see, part of it is positive and the other half goes to 0. That's why we call it return to 0. In this line code, symbols 1 is represented by a rectangular pulse of amplitude A for half of the bit width, and the remaining goes to 0, the other half. 0 is represented by transmitting no pulse, just 0. The disadvantage of this line code is that it requires 3 dB more power than polar return to 0. Compared to polar return to 0, this requires 3 dB more power. Of course, when you calculate the DC value and this, you will find out that it has a DC value and you cannot get rid of it. The advantage of this scheme, on the other hand, this line code contains a delta function at f equal 0 plus minus 1 over TB in the power spectrum. If you take the Fourier transform of this line code, you will find out that you have something like delta at 0, 1 plus 1 over TB plus 1 over 2 TB and so on and so forth. That's why this can be used for timing recovery at the receiver. It can be used as a clocking signal for recovering your communication. Bipolar return to 0, this is another form. We talked about unipolar, polar, we have bipolar. What does bipolar mean? Bipolar means that the first one in your sequence, in your binary sequence, you represent it by a pulse that's positive. The second one, digit 1 that comes in your sequence, you represent it by a negative pulse. And you go on. Positive, negative, positive, negative, positive, negative. That's why it's bipolar, like bi-weekly. Bi-monthly means each 2 weeks, each 2 months, something like this. It changes, it's flat. In this line code, symbol 1 is represented by plus A and minus A for half symbol width. Half symbol width. The other half goes to 0. For example, what's the bit sequence that's represented by this electrical signal? 0, 1. What's this? Again 1, because this is bipolar. The first one is positive, the next one is negative. Then 0, then 1, 0, 0, and 1. Advantage of this line code is that the power spectrum of the transmitted signal has no DC component. If you can see, if you average this signal, find the expectation, you will find out that it's 0. Because this cancel this cancel this. Assume you have fully random signal where the number of zeros almost equal the number of ones. This code is sometimes called alternate mark inversion, the other name for it, instead of bipolar return to 0. So after that we have Manchester code. We call it a split phase code. In this code, 0 is represented by this pulse. This is 0. You start from minus A and you go to plus A. And here half of the duration and here half of the duration. You start from negative and go to positive. And if 1 comes, you start from positive and you go to negative. Half of it will be. So for the case where you have one, it starts from here, from positive, go down to negative, and here another half. So this represents 1. This represents 0. So if I give you a sequence like this, 1, 1, 0, 1, and tells you represent find the electrical signal that represents this sequence if you use Manchester code. What do you do? You just know that the Manchester code represents 1 pi starting from positive, going to negative, and go up. Yes, this is it. This is 1. This is 1. Then again, you have another one. You have 0 now. 0 is like this. And you have 1. Now you just connect them with each other. You end up having your signal, the signal that represents your data bits. So something like this. So you need to know the mapping, how each line code is mapped, what's the relationship between the data bits, zeros and ones, and the signals that are representing them. So the advantage of this line code is that the power spectrum of the transmitted signal has no DC component, which is very good for saving power for Internet of Things application. Also, this line code is self-clocking. Self-clocking, which means that it can be used for synchronization. Now, these are the basic types of line codes which are used to represent your data bits, the one you produce from your PCM modulator, pulse code modulator. And each one of them has some advantages and some disadvantages. You need to know several things. First, you need to know how to represent a binary sequence using these line codes. Second, if I give you a signal, you need to know what type of bits are carried or represented by this signal. Third, if I give you an application or give you a signal and tells you this signal is suitable for which application, for Internet of Things or machine type communication, or map the requirements to the signal representation of your data sequence. These are the key 3 requirements that you need to know about this, and mostly we will be asking about these things. So after that, we have differential encoding. Why do we use differential encoding? For many reasons. The first one is for the cases where you don't require perfect synchronization between the transmitter and receiver. The phase of the carrier at the demodulator might differ from the phase of the carrier at the modulator. So in such cases where you have difference between the phases of the carrier at the receiver and the carrier at the transmitter, you cannot use normal modulation schemes. You need to use something differential, because this produces non-coherency, and non-coherency kills your communication if you don't handle it. Synchronization, perfect synchronization is must in communication systems in order to be able to recover your data back. In case you don't want to do synchronization, you don't care about it, then you must use something called differential modulation. Example of differential, we have differential encoding, which is motivated and inspired from PCM. Suppose I give you a signal like this. Yes, this is the signal I give it to you, and data bits, of course. And I want this to be transmitted using differential encoding. So you tell me, okay, you gave me this sequence 0, 1, 1, 0, 1, 0, 0, 1. In order to do differential modulation, I must use a reference bit, and I will use 1 as a reference bit, or you can use 0. Now, differential modulation, differential encoding works like this. If 0 comes, then you will make a change in your signal. A change means if your signal is going like this, when 0 comes, you make a change, you go down. When 1 comes, you stay down. 1 comes, stay down. 0 comes, make change, make transition, go up. 0 comes, again, make a transition, go down, and so on and so forth. So now you have 1 as a reference. This is 1. This is how you represent 1. Now 0 comes, you must make transition, change. The signal goes to 0. 1 comes. If 1 comes, no transition, no changes. You stay as you are. Go straight. Stay at 0. Again, another 1 comes. Remain at 0. Go straight. 0 comes. When 0 comes, you must make transition. The transition, you are allowed to make transition above 0. So you go up. This is what 0. This is due to 0. 1 comes. Remain straight. 0 comes, make transition. 0 comes again, make transition. 1 comes, remain as you are, and so on and so forth. At the receiver is very easy. It doesn't require the channel information, doesn't require to have synchronization between the phases, doesn't require complex decoder. Just the receiver. Okay, this is, transmitter, please tell me which bit you considered as your reference. The transmitter tells the receiver, I used 1. The receiver uses 1. So after that, and this is 1. After that, okay, the receiver sees that there is a transition here. Whenever there is edge, means a transition. Then this means that if it was 1, this 0. After that, there is no transition means 1, 1. There is transition here, 0. No transition, 1. Transition, 0, 0, 1. You decode your signal. See, the receiver is able to decode his signal easily, without much difficulty, without the requirement of the channel information, without the requirement of phase information, without too much complex circuits. So it's fantastic. But the problem with this, it's more sensitive to noise and error propagation. If you make an error in 1, suppose you make an error in this, in here. This you detected it 0 instead of 1. Then all the other bits that come after that will be an error. We call this error propagation. So if you make 1 error, you kill your packet. You are a single error, like as if in the exams when we bring a question and all the other parts depends on the first part. If you are not able to solve the first part, you cannot solve the others. This modulation is just like this. If you make any mistake in any of the first parts, you definitely will make mistakes in the remaining ones. That's the bad thing about this modulation. Oh, what's the solution for this? We call this error propagation. What's the solution? What do you think? Propose the solution. Reduce the block size. For example, block by block, and each block contains 4 bits, for example. So if you make an error, you make an error within the block. And again, you start again a new block. But if you apply differential encoding for your whole packet, if 1 bit in error, your whole packet in error. But for sub-block, and make them small, you have a chance to correct yourself at the beginning of each block, to start again, fresh, with no mistakes. Yes, is that clear? This is very important, very useful, and it's used in many practical communication systems. How do you generate this? What type of circuits you use? Differential encoding process can be performed by using XOR operation. Very simple. here we understand the logic of it, the physics. How do we, by logic, we can, if there is change, you make transition. But in digital computer systems, how do you perform that? By XOR operation. You get your current data bit with the previous one. The previous one is the reference, actually. The first one is the reference. You XOR them with each other, and the result yi. And then again, you take the previous yi, and you XOR it with the current xi, and you produce your sequence. This is the transmitter, and this is the transmitter circuit, and this is the receiver RX circuit. Clear? I think it's not difficult, but it's very important to understand how to generate this, whether at the transmitter or at the receiver. What are the key advantages of differential encoding? We mentioned some of them, but in the demodulation of PBSK, for example, the carrier in the demodulator must have the same phase as the carrier in the demodulator. I just mentioned that. If a phase error is presented in the carrier demodulator, the received data bits are inverted if there is a single phase error. Differential encoding, this is the key advantage. You must highlight this and comprehend it, understand it. Differential encoding ensures that the correct data bits are received whether the data bits stream inverted or not. That's the good thing about it. That's why it doesn't require synchronization. Application of differential encoding, where do you use it? This type of modulation is used in satellite and radio, relay communication, with passband modulation schemes such as PBSK and quadrature amplitude modulation. On the other hand, this modulation has some disadvantages. The disadvantage of differential encoding is the error multiplication, error propagation, the one I just explained. Yes, error propagation, if I bring it in the exam and tell you, explain it to me, or what's it, or how it happens, and what's the solution for it, you must be able to answer this. If an error occurs to one bit during transmission, then the two bits would be interrupted incorrectly in the receiver. Yes, and this goes on. So this was the information that I wanted to talk about in this lecture.